In this video, we're going over the recursive approach of stone games. So Alex and Lee play a game with pile of stones. There are an even number of piles arranged in a row, and each pile has a positive integer number of stones, piles I. The objective of the game is to end with the most stones, and there are odd number of stones, so there are no ties. Alex and Lee will take turns, and Alex will be starting first. And each turn, a player will be taking the entire pile of stones from either the beginning or the end of the row. And then this will continue on until there are no more stones left. And then, assuming both players plays optimally, return true only if Alex wins the game. In our first example, we're given this array 5, 3, 4, 5, and Alex can pick the first stone, and then Lee will only have the following stones left, so he can pick 3 or 5. And in either case, Alex will always get more stones than Lee. Let's go over the thought process. So we are given an array of stones. Each player is only allowed to retrieve stones from either ends of the array. This means we can have 2 pointers, I and j, to indicate the current 2 indices that the current player can retrieve stones from. Now, we can keep track of the current score of the game. And all of the points that Alex gained, or all of the stones, in this case, that Alex gained, we can increment stones by, let's say Alex get X stones, we can increment stones by X. Then all of the stones, which we'll call Y, that Lee gained, we can decrement. We'll increment score by X. And then in this case, we'll decrement score by X, by Y. Now this means Alex will want score to be as positive as possible. And this means Lee will want score to be as negative as possible. Now, if the final results score is greater than 0, this means Alex has won. Because Alex wants the score to be as positive as possible, and Lee wants the score to be as negative as possible. This means if the final score is greater than 0, that means Alex has won. Now let's go over the pseudocode. So we're going to implement the recursive approach. Now what parameters do we need? We'll need piles, the input array, and then we have our P, the current player. It'll be initially 0. We can have 0 to represent Alex and 1 to represent Lee. And then we can have the current I, the current left boundary, and j, the current right boundary that the current player can retrieve stones from. Now what's the base case? If I is greater than j, this means there are no stones left. If there are no stones left, that means the score will be 0, so we can just return 0. And each of the recursive call, if p is equal to 0, this means we're currently at Alex. We want the score to be as positive as possible. And also, if Alex picks a stone or a pile of stones, it will increment the current score by the number of stones that he have gotten. So we're going to recursively find the score as 1 if Alex picked from the left side. If he picked from the left side, the current player turns to 1, and then we'll increment I by 1. Then we're going to recursively find the score as 2 if Alex pick from the right side. If he pick from the right side, the player still goes to 1, and our j gets to decrement by 1 because we're moving toward the center. Then we can return the maximum value between S1 plus the current pile, or S2 plus the current pile on the right side. This is because he wants the score to be as positive as possible. That's why we return the maximum value between the two possible scores. Else, this means P is equal to 1, it's Lee's turn, and he wants the score to be as negative as possible. Also, all of the pile of stones that Lee gets will decrement the score. Now we're going to recursively find the score if Lee picks from the left side. If Lee picks from the left side, the player will go back to 0, and then we'll move our left pointer to the right by 1 place. And then we can recursively find the score if Lee picks from the right side. The player changes to 0, and then we'll move our right pointer toward the center. Then we can return the minimum value between S1 minus the pile, because all of the piles of stones that Lee gets will decrement the score, and also the score if Lee picks from the right side. And then we'll return the minimum value because Lee wants the score to be as small as possible, as negative as possible. Now, we'll only return true if the results of the recursive call is greater than 0. This means Alex has won. Else, we'll return false. Now let's go over the time and space complexity. For the time complexity, we get O of 2 to the n, where n is the length of the input array. This is because each recursive call has up to 2 choices and a depth of n. Space complexity, we get O of n. This is the recursive call stack memory. Now let's go over the code. So we are going to be implementing our recursive approach. We're going to return stone game, pass in the piles, the current player, initially 0 for Alex, the current left boundary, and the current right boundary. And if the resulting score is greater than 0, this means Alex has won. Now let's create our recursive helper method, pass in our input piles, the left boundary, and the right boundary. Oh, we also need the player. Now what's the base case? If I is greater than j, this means there are no more stones left. If there are no more stones, the initial score will be equal to 0. So can return 0. Now if p is equal to 0, this means it's currently Alex's turn, and he wants to make the score as positive as possible. So I want to return the maximum score of picking from the left side and picking from the right side. So if he picks from the left side, the player changes to Lee's turn. We're going to increment our left boundary by 1, and then we'll increment by the number of piles that he have gotten. And also the score if he picks from the right side, which will mean decrement the right pointer by 1 and increment by the amount of stones that he've gotten from the right side. Else is currently Lee's turn, and he wants to minimize the score. So we can return the minimum score if he picks from the left side. If he picks from the left side, we'll first take the minimum. Left side, the player changes back to 0 because the next turn is Alex's turn. And then we're going to increment by 1 still, and then we're going to decrement by the amount of stones that I've gotten, because all of the stones that Lee gets will decrement the score. And also the amount of stones if you pick from the right side. Okay, we've got our TOE error. So this approach is not efficient enough due to overlapping recursive calls. In the next video, we'll be going over the memorization approach of Stone Game, where we perform an optimization to the recursive approach. Let me know if any questions in the comment section below.